So, dear colleagues, today we are starting our set of our scientific seminars that we are going to hold during all this summertime, from today and up to August 30. Each week we will have 1 or 2 presentations by our lab members and by some invited speakers. So we are very happy that you all are here now. And we invite you to other events that we're going to hold. So this week we will also have 2 more presentations. And today we have a presentation of our leading scientific fellow, Vladimir Batagelj, on multi-way networks. So these are exactly the new developments in network analysis, and we are very happy that we have an opportunity to listen to this presentation in our seminar. So, Vlado, please.
Yeah, thank you, Dasha. So I put on chat a link to the slides. So if somebody would like to have its own copy, then you can download from that link. So the topic for today is multi-way networks. And this is a topic that I started to work at it last, I think, November. But I worked on this topic already before, but then I didn't saw any interesting ideas, so I left it for some time. And last year we had in Porto IFCS conference. This is International Federation of Classification Societies. It's a main conference in the field of clustering and multivariate analysis. And at that conference, my friends from Italy were presenting an analysis of multi-way network about Italian students' mobility. I was listening to that talk, and I found it quite interesting. And then after the talk, we talked with my Italian friends, and they asked me whether I have some additional idea and so on. And I said, okay, if you send me the data, I will try to do something more. And so they sent me the data, but then I was quite busy for 2 or 3 months. So I started to think about their data, I think in November last year. Now, let's first look at their data. So they are a typical example of so-called multi-way networks. The data consist of quadruples of ways. So ways are essentially a kind of variables of categorical or ordinal nature. So in their case, we have 4 ways: the province, the university, study program, and year. And they have an additional information. They have an additional information about the weight that corresponds to such a quadruple. And this weight is counting how many students from a given province selected to study at selected university in a given year and to study a selected program. So this is describing essentially for selected years how students from some province selected a study program at some university. For instance, here I have some examples. So their original data look like this. So we have such lines. There are 37,205 such lines, and each line consists of province, university, studying program, year, and then the weight telling us how many students selected this option. Now, when we are working in with such data, for instance, here we have this nominal or categorical data, or the same is true for ordinal. They are usually transformed into numbers. So this is called factorization. So this means that, for instance, to Bikoka, we assign number 1. Maybe here, if you look to this one. So to Bikoka, we assign number 1. To Bocconi is assigned number 2. Foscari is assigned number 3, and so on. And this is done for all the variables. For instance, to the year 2008, we again assign number 1, and to the year 2017, we assign number 4. So usual transformation is the so-called factorization. In R, you have a special command called factor, and you have to specify levels if you want to have the encoding that is determined by a list of values. So this is the typical example of so-called multi-way weighted network, because we have here also a weight. Now, the approach that was used by my Italian colleagues was the following. They decided to split the data into 4 networks. Essentially, the basic idea was to reduce the analysis of this multi-way network to standard networks. In their case, a 2-mode network. In this case, to a 2-mode network. So what they did, the first thing they did, they split, because there are only 4 years, 2008, 2011, 2014, and 2017. So they split the data to this data for each year, and after that they still had 3-dimensional, so there were 3 ways remaining. Now, to get rid of another way, they decided to join 2 ways into a single way. So they took university and program and created a new value. For instance, Bikoka and Bikoka Edu. These are now 2 different values, but a single way. So they produced a network on provinces and combined way that consists of pairs determined by university and program. And in this way, they obtained a 2-mode network, and then they analyzed the 2-mode network, and that was essentially the topic they presented at the conference. Now, when I got their data, I first transformed the data into using R into PAEC format, and then I was playing a bit with PAEC. But then I decided that maybe the reduction to networks is maybe not the best idea, but maybe there could be some other methods that can lead to something interesting. So I decided to first transform their data into R and save that data in JSON format, so that it's easy then to use either R or Python or some other programming language to when you are trying to do some analytic procedures. So this was the first phase. So I transformed into a special R representation, and then in JSON format. And then I was looking a bit around about their data and on the Wikipedia and other sources. So I obtained some additional data about provinces, mainly about the provinces. And so I extended their data with this additional data. Now, let's try to formalize the notion of multi-way networks. So we call a weighted multi-way network structure that consists of three components. The first one, V, is called a set of nodes. But this set of nodes is a bit different than in traditional way, because it consists of K subsets, V1, V2, up to Vk. And altogether, so the nodes are split into this list of K different subsets. And on these nodes, then we create the links. The second set, L, is set of links. And then we have also a weight W, which assigns to each link a real number. Now, the set of nodes and set of links are linked by incidence function, which this incidence function assigns to each link 4 nodes, one from each of these K subsets. So the first node is from the first subset, the second is from the second subset, and so on. The kth is from the kth subset. So essentially, this incidence function assigns to each link a k-tuple of nodes. Often we call these nodes end nodes of a link E. So E1 is a component from this subset V1. E2 is a component, or is a node from the set of V2, and up to EK is from the subset VK. Now, often these sets are different, but it can also happen that 2 or several of them are equal. Now, if it happens that some of these sets are equal, so that for different I and j, set Vi equals to set Vj, we say that Vi and Vj are of the same mode. So that we know this notion of mode also from two-mode networks. So, for instance, in ordinary network is a two-way, because there are essentially the first node and the second node of a link are from the same set usually. But if in two-mode network, the first set and the second set are usually different. So in this case, we are speaking about two-way and two-mode network in the case of or traditional two-mode networks. So this is a kind of generalization of these ideas of two-mode networks. Now, in a general multi-way network, we can know additional data about nodes or links. So we extend this notation in general case to a set of P of properties of nodes. A node property assigns to a selected node elements from selected node sets set Vi some values from set, let us say SP, S that corresponds to this property. And the same is true for weights. Weights are functions that assigns to each link the corresponding weight. So the mapping the set of links into some set of possible values. And another thing, assume that we have some subset of links, L prime. Then we introduce the notation Vi of L prime. This is the set of all endpoints from set Vi that are an end node of an edge inside L prime. Now, in general, a multi-way network, it can happen that there exist several links that have the same set of to which the same k-tuple corresponds. And that's in general possible. But if this is not possible, if in a given network, we always it always holds that if one link is different from the other link, so if you have two different links, then also the corresponding k-tuples are different. In such cases, we call a multi-way network. We say that multi-way network is simple. Now, another notion which is useful is a notion of subnetwork. So if we have a multi-way network VLPW, then a multi-way network V prime, L prime, P prime, and W prime. We say that this one is a subnetwork of this one, if and only if it can be obtained from N, from original network, in the following ways. We can either remove some nodes, but if a node is removed, then also all links in E, links E from L that contain it are removed. So when we are removing a node, we remove also all links, other links that, or links in which this node appears. Then we can remove some links. We can even remove some ways. And we can remove some properties from P or W. So these are the ways we can transform original network And what we obtain after these operations is called a subnetwork. We could also introduce the notion of homomorphism, isomorphism of multiway networks, but we will not, today we will not need these notions, so I will skip this part. So another notion we also need is a notion of a star. This is a generalization of star in ordinary networks, and we say that for a node U from Vi, we said that the star of a node U consists of all links that contain node U as an end node. And this is the same as in traditional network analysis, is just an extension of idea to multiway networks. Now, how to represent these multiway networks in R? I decided to make the following structure. So I decided to treat multiway networks as a list that consists of 6 basic components. The first one is just called format and contains a string MW nets, which says that this list is describing a multiway network. And then there are 5 other fields. The first field is so-called info field. This field is not intended for analysis, but it's intended for users and contains the metadata about a given multiway network. I will show you later its structure. Then these are then the data fields. The first is a list of ways. It consists only of names of the ways. Then the basic 2 fields are the field nodes, which contains a list of ways data frames. I will show you immediately how it looks this. And the field links that contains a data frame of links and weights. And as I mentioned before, we can have also some additional data and that can be useful in analysis, and we can put this additional data into the field data, which contains a list of additional data, and we can access this data when needed. Now, here is an example of how this structure looks for the Italian students' mobility data set. So here we have first the list I called it here in RMN, was the label of the variable that contains this multiway network. And we have a list of 6 elements. The first element is that MW nets, and then we have info. I told you these are metadata. So here we have name of the network, and I called it students. Then some descriptive title, which says student mobility data in Italian universities for the years. And then data were collected by Genova, Giordano, Ragozzini, and Vitale. this description was created by me, and the date was November 6, 2022. And this is these are the metadata. You can add additional data. For instance, we could, if there's some page on the internet where you can get the original data, you could put that information also in this info, or as I decided later, I put here also a kind of trace information. So whenever you apply some transformation on the data, the new version gets here an additional field trace, and then you have different events that are describing the history of changes of the data. So you can always reconstruct how some partial result was obtained. Now, the third field is ways. Here we have just the list of ways. I named them pro, univ, proc, and year. And here the values are longer descriptive names of these 4 ways. So we have 4 ways, and these are descriptions. But these 4 ways should now repeat in the nodes and links. So in nodes, we have to provide the data about each of these ways. So we have, for instance, for provinces, we have a list, we have ID, and this ID contains a list of possible values, essentially a list of abbreviations of names of Italian provinces. But then I looked to the Wikipedia, and from Wikipedia I obtained some additional data about provinces. So we have also the information about the type of province, then long name of province, name of the capital of the province, information about the region to which a province belongs, then ID of the region, then information about the macro region, number of inhabitants, and the area of the province. So these are additional information that are related to this first way province. The second way is university, and here we have ID. It's a kind of short name, and then we have also a long name. Here there is no nice example to see a big difference. For instance, Biomedico, and here we have Campus Biomedico. So when you are analyzing some data, if you have very long names, it turns out it's very difficult to produce nice looking printouts or visualizations. So because of this, I decided to use for IDs a kind of short names or abbreviations for the corresponding values. But beside this, I decided also to provide a longer names if for some other occasions where you need to be more understandable. and in that cases you can print out or display a long name. Here then we have programs, and here we have again abbreviations, and here, for instance, this AFFV essentially means agriculture, forestry, fisheries, and veterinary, and so on. So this is about the programs, and years we only have the corresponding IDs. There are 4 years: 2008, 2011, 2014, and 2017. So this is the description of nodes, node sets. So there are 4. And now we have the next field is field links, which contains links. So these quadruples, this column here represents the corresponding quadruple. Yeah? And the first component is telling us about the province, about the province, the second about university, third about the program, and fourth about the year. And after that, we have W, which is the corresponding weight. So, but we know from this information here that the weights are these 4. So in this list, these 4 are weights, and this one is the weight. And then I had included also some additional data, and this was about the regions, names of the short abbreviations for the regions and long names of the regions. So what are the limitations or restrictions in this description? The first one is that the names that are listed here in the ways should repeat here, 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 and here. So these 4 are repeated here on these places, and also here in the links. We should use the same names. Then in these nodes, each node, each subfield should contain ID variable or column. So here we have ID, here we have ID, here we have ID, and here we have ID. Because the routines I developed are using these IDs, and the data frame links should contain at least 1 weight column. And this is also true because we have this W here, and this is the weight. Now I created many multi-way networks, and if you click to these links here, you get the descriptions how this data were converted into multi-way networks. Later I will show you also the page where you can get the data, and if you want to play with the system. Now I will skip this, but I will only comment on this slide. So there is a lot of multi-way networks which are, or other, in other way, so-called multi-relational, or some are calling them also multiplex networks, are a special example of multi-way networks. Why? Because multi-relational networks are essentially three-way networks. So it's an example which is, it turns out that if you look to many repositories and so on, you will find many such multi-relational networks available. And there is quite a nice collection which was created by Manlio de Domenico. If we click here, you can, oh, excuse me. And so you see I'm only at the beginning of the list. So it's a long list of examples of this multi-way networks. And besides this Manlio de Domenico list, there are many other sources where you can find data from which you can construct the multi-way network. So there are quite several examples. The problem is that most of them are only three-way. But what would be interesting would be to have some nice examples of, let us say, at least 4 or 5 ways networks. And for such multi-way networks, I'm still searching for. Another comment, there exists another approach, which is also called multi-way analysis. There exists even a book on this topic, Applied Multi-Way Data Analysis. In this approach, essentially we have similar idea of the data. So we have in most cases they are dealing with three-way, but things can be generalized to multi-way structures. The difference is in the approach. What this multi-way analysis is doing, they are trying to apply ideas from traditional multivariate analysis. It means linear algebra, eigenvectors, eigenvalues, and so on, and apply this to analysis of such multi-way arrays. If you go to Google and enter keywords like Tucker, Parafac, SIM, PCA, models, and so on, you will get several papers on this topic. So we will not work in this direction. We will continue in another more combinatorial direction. So this we started to think about these problems already in 2006, when with Anushka and Pat, we developed a so-called indirect approach for block modeling of binary three-way networks. And here are some pictures from that paper. The idea is that the data are three-way. So we have three different ways. And there exist some classical data sets of this type. One is Lazega lawyers, and the other one is Krakart. I don't remember exactly what is the topic. So we developed a method, and then here I'm showing how we approached the testing of the developed methods. So here we have an ideal partitioning into blocks. So we have this gray block, red block, again gray block, and so it turns out that they ideally so all the blocks are either empty or a complete, so-called complete blocks. So such a configuration was randomized. So here I have the same configuration as is here, but randomized. And then using the developed methods, we tried to re-establish this situation, and it turned out that for these ideal situations, it works perfectly. Then we applied the developed methods to real. I think this one is corresponds to Krakart's data, and again we see that the method discovered some kind of blocks, but the data were not ideal, so we cannot see so nicely structured blocks inside the corresponding result. But it seems that methods are working quite well. Now, getting this Italian data, I started to think about other approaches to analysis of multi-way networks. And so I started to develop a package which is called MW Nets. It's available on this on GitHub on this link, and on the same maybe I can show you. So if I click here, you get to the GitHub, and here you have this paper from 2006, and here we have some subdirectories. Maybe the most interesting is this data. Here I prepared a list of several networks that I found on the internet and converted into a format that I described to you. Unfortunately, the Italian students' data, I have no permission to make it accessible to the public. So all others you can download, but for students, I'm still waiting for permission to make it accessible. So we will close this. Now, this package works relatively well, but there is always a warning. It's a work in progress. So it can happen that there are still some bug inside the procedures, or it can happen that at for certain data will not behave as expected. So if you will play with and you find some something that is not working properly, please inform me so that I will correct the code. Now, I don't have time to go through in details through these functions. So I implemented several functions. One is the reordering of ways. Then a function that takes from multi-way network a slice. It means it takes out a subnetwork satisfying some conditions. Then we can extract, it's similar to slice, but in a bit more regular way, we can extract some subnetwork. A very useful operation turns out to be so-called flattening. Flattening means that I decided that I will preserve only some of the ways, but all other ways are just flattened. It means that they are reduced to the selected ways, and it means that they disappear, but during this process, their values are aggregated in some way. We are projecting everything or to the selected ways. Then we can also reorder links, and we can. This is the operation that my Italian friends were using in their presentation in Porto. It's a join ways. It means I select two ways and combine them, the values, into a single way. Then I will skip this how to transform data from paper into the JSON format. Now, many of these multi-way networks are created from data frames. And to make transformation easy, I wrote a function, data frame to multi-way network, which transforms a data frame into the basic structure of the corresponding multi-way network, which can then be further, to which we can later add some additional data and so on. But the basic structure is produced by this function. How this can be used can be seen from this link. Here I found on Kaggle site a description of 120 years of Olympic history, and there is a total list of all the results of winners on Olympic Games, and this is a data frame, and this data frame I transformed into a multi-way network about Summer Olympic medals till 2016. And most of the job was done using this function. Now another function which turned out quite useful is the visualization of multiway networks in as a 3D layout. Now we had such visualization already here, so this was a 3D visualization of three-way network. But it turned out that solution I was using here doesn't work anymore because the support, I was using some some chemical program, and they stopped to support it. So I had to do the job again. So this time I said maybe the web technologies are more reliable, and I turned to X3D format. This is a web standard for description of 3D layouts. And so I prepared a function which presents selected three ways of a given multi-way network in 3D space. So now when we produce such a layout, we need to have some special viewer to inspect it, such a layout. And I found a program which is called View 3D Scene, quite a nice viewer. It's essentially a byproduct of some game development tools, but it works quite nicely. After that, I discovered that there is maybe even better solution, that essentially we don't need to have special programs, but there exists a solution which is called X3DOM. X3DOM is JavaScript-based library which allows you to include such X3D descriptions directly in web pages. And using this library, you can inspect them. So this is essentially my preferred solution. So the same description can be viewed either as a web page or using this 3D layout inspection programs. I will skip the rest of this page, and here we have an example. So just to see how this visualization works or inspection works, this is a visualization of this Robbins Bank. This is a three-way network from a paper by Pattison, Wasserman, Robinson, Kanfer, and they are describing three. So the dimensions are employees in a bank. So we have bank branch manager, deputy manager, advisor, service advisor 1, advisor 2, advisor 3, and then you have 6 tellers. And you have 4 relations: advice seeking, close friendship, satisfying interaction, and confiding. and the data were published in a paper, and then I converted this into three-way network description. Now, if we go now here, if we click to this link, we get a 3D visualization. And now, using the wheel on the mouse, we can zoom in and out. And now what we can do, we can rotate. The structure. So here we have these 4 different relations. And now observing this structure, we can see how one relation relates to the other. So whether there are some regularities and so on. Maybe, but one of the main questions when we are dealing with 3D visualization is what is the meaning of different cubes? So cubes are representing triples, these triples. So, but what is the meaning of this triple? There are no coordinates here. Now, one option would be to write somewhere the names of coordinates, but it turns out that it's not very readable. So it turned out that there is an option that in the description we assign to each cube or each, in general, graphical element a kind of the description. And when we click on this, this description is then displayed. So for instance, if I click to this cube here, I get here up that this a description that this is link number 75, describing that Service Advisor 3 has a satisfying relation with Service Advisor 1. And weight is 1 because here we don't have real weights. And so now if I'm clicking, you see here we have Service Advisor 2, Service Advisor 1, this is the Deputy Manager, and this is Service Advisor 3. So, but all are related to Service Advisor 1. So it means that in this direction we have Service Advisor 1, and these are Service Advisor 3, Deputy Manager, Service Advisor 2, Teller 1, Teller 2, this is Teller 3. So these are in this direction down. So using this clicking on selected cubes, we can then inspect the picture and get an information or get an intuition about what's going on. So here we see that if we look to this, we have Service Advisor 2, Service Deputy Manager, Service Advisor 1, and if I click here, no, this is Service Advisor 3, and this is Service Advisor 1. So these are the essentially Deputy Manager and 3 Service Advisors. Now, if I click here, I get this Branch Manager. So we see that in this case, for this satisfying the this 4 persons, 3 Service Advisors and and I think I forgot. I think it's the deputy manager. Yeah, and deputy manager are, but without this service advisor one, are in good relation, satisfying relation with all. Here we have these empty places, but these empty places essentially corresponds to the relation of a person with itself. So these are then empty, and so on. So in this way, we can inspect the structure and get some intuition about the network. So I will close this. Now, when we are producing such visualizations, we know already from matrix representation of ordinary networks that we have still a lot of freedom. So what we can do, this picture can depend heavily on the ordering of the values. So I can order on each of these three ways, and different orderings will produce different visualizations. And if the ordering is selected in the right way, sometimes we can get some patterns inside the structure. Now, how to determine the orderings? Often what we are doing is either to take some property of selected way and order the elements according to the increasing or decreasing values of that property, or other approach, which is also often used, is to do clustering on each of the ways. Now the question is how to do clustering. For clustering, we need some dissimilarity measure. And here I got the idea that essentially maybe we can generalize the idea of projections of two-mode networks. So if I have two-mode networks on sets U and V, which is described by a matrix W, then we know that we can usually analyze two-mode net. One of the approaches to analyze two-mode networks is to project this two-mode matrix into a selected set, either U or V. Now, if I want to make a projection to set U, I take a matrix V and multiply it by its transpose. If I want to make a projection to the second set, V, then I take the transpose of the matrix W and multiply it by itself. And in this way, I obtain a matrix which is measuring how well, essentially, how often elements essentially it's measuring the number of common neighbors from the other set for the nodes U and T. And this now, if you look how this element CUT is computed, we use this definition of product, and now if we make a transposition here, it means that I have to interchange the T and V, so I get this expression. So this CUT is a sum of products of weights on UV and weight on TV, summed over all nodes V from the second set. And then using these CUTs, we can define so-called Salton index. And this can be easily generalized. So if this V and T are not just nodes, but k-1 tuples of nodes, we get a generalization. So we introduced projection, let us say, to this for ease of notation, to the set V1, and the corresponding element of the matrix is determined in the same way as in the case of two-mode networks, except, so we have U and T here, and this is the V. So instead of a single node, we have here this k-1 tuples. So I'm summing over all k-1 tuples. But usually many of these tuples are missing. So I'm considering only those that have non-zero value, and it turns out that this can be done very efficiently. Now, in this way, I compute for each node U and T from V1 their similarity. How similar are they? Essentially, how often they share the neighbors. And this is then, this would be the interpretation if the weights would be binary, so the value of weight would be 1. If the value is not 1, we just generalize this idea as in two-mode networks. And now, using these computed values PUT, we can define for nodes U and T the corresponding Salton index as is defined by this expression. So we take the computed similarity UT, and then we divide this by, let us say, size of node U and size of node T. This is Salton index is often called also cosine index, because it turns out that in ordinary interpretation, it's when we are in n-dimensional space, it corresponds to the cosine of the corresponding cosine, and it's very easy then to show that this Salton index is defined on the interval from -1 to 1. It's symmetric, so Salton index of U to T is the same as the index from T to U. For UU equals to 1, and if the weight is non-negative, so if the values are non-negative, then the Salton index is on the interval from 0 to 1. So I will skip this to other properties. So it's a way how to define a measure of similarity of two nodes in a selected way. And I applied this to now to do clustering. We still need to transform this similarity into a dissimilarity, because clustering procedures are usually defined on dissimilarities. But this is relatively easy, because if you have a similarity from 0 to 1, just taking 1 minus s, you get the inverse, and you get so 1 goes to 0 and 0 goes to 1. So you get a measure which is dissimilarity has value 0 when for UU, and has value 1 when this Salton index has value 0. So you get a dissimilarity measure, and this dissimilarity measure can then be used in clustering procedure. You get then the partition, and then according to that, or dendrogram, and according to that dendrogram, you reorder the values of the way, and you get then the ordering needed for visualization. So for instance, here I have the corresponding picture for Italian students' mobility. Here is the dendrogram. Here we have different universities, and it turns out that the right universities come together. So the clustering is quite satisfying. And here I have problems with so here we get different all these universities, programs for a selected year, and provinces, universities, and programs. And what we see here, we notice that there are some groups of that appear inside this visualization, and then we can let's go a bit up. So for instance, if I click here, I see that this is from province of Mantua, University of Parma, and the program is social science, journalism, and informatics, and 81 students moved there. Now, clicking on different, we see that essentially a column here corresponds to Mantova and University of Parma. Now, if I select this one, is again the province is Mantova, but university is Modena. So here we see that students from Mantova are mostly studying in Modena or previously, this one is Parma and Modena. And so now if I look here, so identify the, let us say, a kind of visual groups, and then inspecting the cubes, I can see what are the corresponding provinces and universities, and also programs. Another thing which is very comes out quite interesting is that we have some such long lines, heavy lines. And now if I click, for instance, on this, maybe I will go out a bit. You see, you get such lines. And now if you look what's, I need to go up to see also. So let's look to this. So here we see we have P Torino, which means Politecnico di Torino. So all this line here essentially also the corresponding plane corresponds to Politecnico di Torino. And it means because you see here we have for all different provinces, we have this cube on this line. It means that this university, Politecnico di Torino, is getting students from all over the country and so on. So it turns out it's quite useful visualization, but I don't have now time to spend more time on this. So I will close this. Yeah. And I will, another option which is quite useful is also recoding. And now I will show you an example, another example, which is about European airports. So here we have the information about the departure airport, which is way 1, arrival airport, which is a second way, and the third way is flight company or line. So there are 450 airports and 37 flight companies or lines. And now to analyze this, I did the clustering and so on, and using the clustering, we get such a picture. And on this picture, what we see is that there are some parts of this space which consist of cubes of the same color. For instance, here we have green area, and there are no other colors, almost no other colors. It means that colors are representing different companies. So here we see that between some airports, there is a single company that is serving that airports. And in the case of this green, turns out that green means Ryanair. So Ryanair is a company that found a kind of niche, and it's serving relations between selected airports, where and among these airports, no other company is serving. And it turns out that there are some other, for instance, here we have this gray part, has the similar role as Ryanair here, and there is another one here up, which has the same property. But if you look to this part here, we see that we have many different colors. And it turns out that this part here corresponds to the main European airports, and the lines are served with many different companies. Now, to identify the most important companies, I decided to, I got the idea that maybe the idea of course can be extended to multi-way networks. I don't have time to go into details, so it turned out that it works, and that we can develop algorithms for computing cores in multi-way networks. And here I have the result. Maybe I have it already here. Yes. So I determined the course in this network of airports, and what I obtained is the following structure. Now, after some looking for a while on this structure, I noticed that this structure is somehow special. And what is very typical for this structure is that you have several crosses. For instance, here I have a pink cross. Here I have light or yellow-green cross. Here I have a brown cross. If I look from this side, here I have a blue cross. Here I have a black cross. Here I have a violet cross, and so on. So the first observation was there are crosses inside this structure. And what is the meaning of these crosses? Essentially, if we look to a cross, so here we have Madrid to Budapest, Budapest. So all this brown correspond to Budapest. If I go to this direction again, we have Budapest. So all these flights are departing or arriving to Budapest airport. And they all belong to Multiway company. And Multiway is a Hungarian air company. So it's you immediately see that essentially it seems that the basic organization is that each or at least most flight companies have their base airports, and they are flying from this. They are serving flights from these base airports. And so I decided to reorder manually the airports in such a way that I'm considering this observation. And now if I go here to structure, I will go immediately to better structure. So there was an intermediate result where I need to do some additional improvement. And here we can then get the final visualization of this airport core. Now, if we look to this representation here, or structure, you see we get something like this. And now if I rotate this, you see that most of the flight are lying on kind of planes. This is one plane, this plane, and if I rotate this, there is another plane. Yeah. So we have essentially two intersecting planes. And now if you look to the what's behind, if we try to interpret the obtained result, so now if I click here, I get Frankfurt Airport to Tegel Airport, Frankfurt. So this line and this line corresponds to Frankfurt. This one to Tegel, you see. So these are Tegel and Tegel. This one is Munich, and this one is so if I go here is Düsseldorf, and this one is Hamburg. So we have Frankfurt, Tegel, Munich, Düsseldorf, and Hamburg. And the company, the white means Lufthansa. So what we can say, Lufthansa is serving flights among or between German airports. But we have white color also here. And if you look here, we see Milan, Malpensa, Milan, Heathrow, and so on. So this, and also this part here, we see that besides the German airports, Lufthansa is serving also Milano airport. So this is the first thing. Then here we can then look to the different for each one. So for instance, this one is we see as Charles de Gaulle. So it's and the air companies Air France. So Air France is serving from Charles de Gaulle airport, and so on. We could identify for each of them. But what's more interesting is if we look this from this side. So here we have flights that are not on the planes, on that pattern, on the crosses, but they are outside. And now let's look which are these so we have here Leonardo da Vinci, Fiumicino, that's Rome airport, and Venice Marco Polo, and the company is EasyJet. So we see that EasyJet is out of this general pattern. So EasyJet is serving flights between, it doesn't have a kind of base airport, but is serving flights between different airports. So one such company is EasyJet. The other one is this brown one. It's NetJets. And then we have this pink one, is Wizz Air. And now we have another brown color here, which is European 80. So we see that essentially reordering the nodes in the right way, we obtain a pattern that gives us an explanation about, or a kind of confirmation of the basic structure of European airports and companies, which says that most of the companies have so-called base airports, and they are serving flights from these base airports. But there are some companies that doesn't follow this scheme, but they are serving, they're how to say, filling the niche and serving flights between different airports. So I think I have to stop here. Thank you for your attention, and if there are some questions, I can try to answer to them.
Vlada, thank you very much. I think it's amazing to look at these structures in this 3D format. Very interesting. Dear colleagues, do you have any questions? Okay, while you are preparing your questions, I think we should ask some questions to Vlado.
No, we are over the time, so...
okay, I think we can stay a little bit longer. But I'd like to ask two questions, actually. One question is for clarification. Sorry.
Yeah.
So you said that multi-relational networks are special kind of three-way.
Multiway. Yes.
Yeah, of multi-way networks. I didn't quite understand this because as I understand this multi-relational networks, this would be like we have two nodes and they have different types of relations between each other,
yes,
like friendship or like helping each other.
These types of relations are just the third nominal variable. So we have values, for instance, friend, money, I don't know what. Yeah.
That would be the third mode, and it will be connected.
The third way, yes.
The third way. Yeah. Okay, okay. Thank you. And then I also wanted to ask you, did you think about some generalization of this type of data analysis to bibliometric networks? Such as you have organizations, then you have
yes, surely,
authors,
you
journals, and so on.
Yeah, you could, but I didn't try yet to do some. I think it's possible. Yeah.
Yeah, I was just thinking that they can be different kind of bases.
For instance, in our examples, we don't have, or what we get from WOS to PAEC, we don't get countries.
Or categories.
For instance, if we would have also the information about countries, then we could have these authors, countries, keywords, maybe would be already three-way network.
Or categories of the disciplines.
Or we can, there are different properties that can be proclaimed as ways. But how to say, I hadn't time to, essentially, at the end I have some conclusions, and one of the, there are many open questions here. So one open question is, what are interesting structural node properties? For instance, we have degrees in or betweenies and so on for traditional networks. Now, what are such properties meaningful and for multi-way networks. I think this is here in this airplanes. I use airports. I used a property which I didn't explain, which is called diversity, which was measuring how many different flight companies are linking to airports. But there are many other properties that can be defined, but how to say it? It's totally open. Another question is, for instance, I was looking to these European social surveys. They have very interesting sociological data. But the problem is that, and most of them are of nominal nature. So there are questionnaires and you have different options. So data are of the right type. But the sets are very small. So the number of different values is, let us say, 3 up to maybe 6 or something like that. So there are not many different values. But the approach that our Italian friends are using to combine 2 such variables into a single variable, in this way you get more larger ranges of values. So this is, for instance, one of the questions I would like to investigate. So can we use this combining of variables into a single variable, what we get in doing this, or in the opposite direction, if you have some numerical variable, you can split it into, you can make a discrete variable, and this discrete variable can be treated as ordinal value. So in this way, you transform a weight into way, and you increase the number of ways. So, but how to say? I don't have enough time to do all these things. So.
Great. But it seems like there are a lot of things that can be done. We have a question from Harani. So I will read it. Thank you for the seminar. You were talking about the distance computation by constructing the matrix. However, what happens when there is an insertion or deletion of a node? Should we construct the matrix again with the edits, or how can this be handled?
No, we do first all the operations. So, and for fixed multi-way network, we then compute these projections, and from projections, then we can get the similarities needed for clustering. So
so it seems like you delete or insert the node for the projected network already.
I don't understand the situation where this could be a problem. So if he can or she can explain more in details what is the problem. What is why he thinks about inserting or deleting a note.
Oh, okay. Let's say a new airport is constructed in Prague.
Yeah, what is if you the network describes a situation as it is. So now, if then, for instance, if in certain year, so if I'm describing for selected year, then there is or there is no airport. I don't need to insert it, but it can, if I have temporal information, then it can happen that in 1 year there is no airport, and on the other year there is an airport there. So, and if there is no airport, there are no flights from that airport, and so this would be you can have the description in which you have all the airports, and because there are no flights to that airports in that year, it means that at that year that airport was not active or even didn't exist yet. Because also some airport can be closed and stop functioning and so on. So, but you put in the set all the networks that appear, and then, if in the case of temporal data, you have for each year different activities, and from there you see what is the real situation.
Mm-hmm. Mm-hmm. Yeah, so Parani answered that it is understood. Super, thank you so much. Okay, great. So I'm really happy that we had this seminar. So we will having some chances to listen to this presentation at some conferences, but I'm really happy that today we managed to provide this lecture to the wider audience. So Vlada, thank you very much.
Thank you
so
for
we will
invitation.
we will be looking forward for new advances in this topic, and probably some of us will try to implement this methodology in practice. Okay, so I will say once again, thank you so much, and I will stop the recording.